Thanks, it's great to be here. People can hear me okay? Um, in the spirit of experimentation, I have never used this presentation software before, but it has the word beautiful.ai. Sort of AI related talk. Let's see how it goes. So this is my abstract as I've rewritten it. You can read it. As you heard, I've mostly worked in the LIGO area, and we recently lost our founding father, Ray Weiss. And he and I have been working together since 1999. And it wasn't like a regular student-professor relationship where the professors sort of said, like, go off and try that stuff. And tell me how I come back in a month. And then the professor's forgotten about it by then. But he had retired at that time. So we were like, it was like a buddy comedy of us traveling around and working in the swamps of Louisiana and that kind of thing. And we've been, so it's like 25 years of working together, and it's a really tough thing to move forward. And, I've been under the mission of this one guy for this entire time. So I'm now in a state of rethinking what directions to do and where should we go. But the main thing I got from Ray was about how do you design experiments and how do you understand what you're doing, and like how do you work through it? Like, do you just randomly throw some stuff together and then mess around and see how that goes, or do you think really carefully and then do it? And if you there's like a story about a story about a story or something, but we were in a Thai restaurant once and I asked him, what's the right, like, how did you come up with this LIGO idea in the first place? Because there's just nothing, and then all of a sudden there's something. I'm not like that. I usually I don't have any original ideas. I usually just take other people's ideas and kind of like stick them together and see if it works. And he said, yeah, that's how everybody does it. But then he told me this story. He said, Bob Dickey, who he was a postdoc of, he said, Bob Dickey did this thing once where he just disappeared from the lab for a few months. And he went home in his garage, and it was like before email, so you couldn't get in contact with him. And he just came up with the idea for the solar oblateness measurement, which I don't want to tell you about it, but it was a really difficult experiment. And he did it in this way that nobody actually does things. He just thought about every little piece of the whole thing, all the systematics and errors and everything, and then just came in with a bunch of drawings and told all his postdocs, like, okay, you're in charge of this and that. And that was the one time that Ray had ever seen somebody kind of just like immaculate conception, a single experiment from nowhere. And that was his attempt to do that in 1972 was the birth of LIGO, basically. Anyway, I don't know how to do that. So this talk is about the fact that basically I can't do that. I don't know how many people can actually do something like that. So instead, I'm talking about a few different things that I've worked on in the past, and they kind of fall under the umbrella of here's a difficult problem. Let's see if we can do some sort of large scale numerical optimization and solve that thing. And I'll give you a few examples of those things. But I thought I'm coming here. This is not like a physics colloquium where I would talk to you about the deep physics of the black hole horizon or something like that. But a real limit to experimental physics, I think, in a lot of different areas is the instability of thin films today. And I have to say, like, as a normal, regular physicist, I'm into black holes and things like that. I find condensed matter physics kind of dull. But as I got into it, it's kind of, I don't know if it's profound, but it's profound-ish, I would say. And so I want to take you on this journey of thin films a little bit to say, it's weird. And if you can solve this problem of what's going on with two-level systems in thin films, it's like, what do you call it? It's that, there's a Disney cartoon where Mickey Mouse hits like 7 flies with 1 stick, that kind of thing. And like, then they say, Mickey Mouse, you're so great, you've done that thing, now you should go kill the giant because you've been able to do this one task. And I think this is like that. If we solve thin films, it'll have a ripple effect over many fields of physics. Important problems. That's mine. So I'll tell you a bit about LIGO and what's going on, and then some optimization I've done in a few experiments, and a little bit, and then getting into this thing about why thin films are the real problem. And then my pitch to you is about how do we actually make the perfect thin film. Okay. Gravitation, this is my only gravity equation. This is only one I know. On the left-hand side, the G means like what's the curvature of space and time. That's the metric. And on the right-hand side is T mu nu, which means that it's like the Maxwell stress energy tensor in E&M, but it's the mass energy tensor for general relativity. And so it has matter, energy, momentum, and things like that in the tensor. And the main thing is there's this big prefactor or tiny prefactor, which in SI units is 10 to the minus 44. So it means like if you want a curvature of 1, it's like a black hole, you have to have that much T. That's a lot of T. Most of us are not capable of doing that. So even things like the moon and the earth and massive systems like that, they make such an infinitesimal curvature of space that it's really hard to measure. And you need experiments like GPB and things like that to really measure this kind of little bit of curvature. So it's not really happening. The events are really powerful. So the curvature is like unity when you smash black holes together, and the energy density is, of course, like the highest you can get. But I guess luckily for us, we don't live in the environment of black holes, so we're not feeling the curvature in our bones. But it happens at distances of like 100 million light years away or something like that. So by the time the waves get to us, and you should just think about it like regular waves. There is a difference between gravitational waves and electromagnetic waves, but I mean, basically waves are waves. Right? They go and like the field goes down like 1/r, and as long as the waves are traveling in 3 spatial dimensions, that's, energy must be conserved and so on. And gravitational waves have 2 polarizations, like light has 2 polarizations. A lot of the things are analogous. But anyway, by the time it gets to us, the waves are really weak, and the strain, which is the stretching of space and time, is of order 10 to the minus 21 for the strongest events that we find. But for the events that we really want to go after, like what happened in the Big Bang, that's more like a 10 to the minus 24 or 25. So we're not there yet, and it sounds like a lot. I mean, if you tell anyone like, invest in my startup company, I'm 10 to the minus 4 of what I need to make a profit. Usually don't want to invest in those things. But LIGO is the story of going through something like 9 orders of magnitude in the last 50 years. So I'm not going to tell you logarithmically, don't extrapolate that much. It's not that good of a story, but there's a few more orders of magnitude to be had before we get into the realm of extraterrestrial technology. So what humans can do is still another factor of 1,000. I hope, So, yeah, isn't it a spectacular presentation? So I just want you to do that again. Okay. So this is how it works. On the top is the diagram of kind of how it works. Is the black holes, the waves come, and there's a laser interferometer. And on the bottom is this thing about noise, basically. So this is frequency on the x-axis, and the y-axis is strain. 10 to the minus 21 means something like the Earth is like 10 to the 7 meters inside on the fixed 10 to 7 meters. And so a strain of 10 to the minus 21 means you get something like 10 to the minus 15 meters of motion across the Earth, which is about the size of a proton. So that sounds dumb, right? But how are you going to detect the size of a proton on Earth or something that's, and yeah, you can't do that actually. So there's a lot of tricks in that number. One has to do with the fact that it says strain per root hertz. And if it wasn't strain, if I said I was measuring something like watts, then it would be watts per hertz, which would mean in a frequency band like a hertz or whatever color filter you have, this is how many watts you can detect. That's kind of what that means. And so this is the square root of a power spectral density. And it's square root just so that the displacement is linear on the y-axis. But that's kind of what it means. This is about the noise of the detector. And it means there's a minimum from like 100 hertz to a kilohertz where we can detect things pretty sensitively. But there's no way that you can just add a proton to the Earth and we'd be able to measure it. So it's not a DC measurement. At DC, the LIGO detectors are not worth much. Or, I mean, I shouldn't say that. They're worth a lot, but they're worth a lot to seismologists, maybe. Like the first astronomy I ever did in my life was also like Ray Weiss and I were at the Hanford detector one weekend with everybody else around, and the detector was drifting a lot. And late that night, as we drove back, we realized, oh, it was just the moon. The moon was on the other side of the mountain and the gravitational pull was stretching the LIGO detector. So I had detected the moon using a few $100 million of government-funded equipment. Good for me. This word cloud is about what are the other sources of noise that matter a lot. And the main thing is there's quantum noise, there's things like seismic and acoustic noise, thermodynamics of the mirrors is the main thing I wanted to talk to you about today. And there's other things, quantum back action and things like that. But the basic idea is this: the laser comes into one side, the space-time strain stretches the arms either together or differentially or some combination of those. And because the laser is noisy, because we don't have perfect lasers, we are kind of insensitive to this kind of common mode stretching of the arms. If we had perfect lasers, the detectors would be way, way better. But if you had a perfect laser, you wouldn't need all of this stuff. You just measure the laser by itself. So that's kind of a trick here. And the signal comes out of the dark port of the Michelson, just like it did for Michelson. So this is just like what Michelson did, except our ether turned out to be real eventually.
Do you mind explaining what you mean by you had a perfect laser by 10?
Yeah, for example, if you had here's a good example. So helium has a super high ionization energy, it's a super strong thing. And it's largely protected from the environment. Also, like the thorium nucleus transitions, which are in the UV, they're extremely protected from the environment. And so those things have a quality factor or a lifetime, which is long enough that you can almost use those things to detect gravitational waves by themselves. I just don't know how to build a laser out of thorium clocks and helium nuclei yet, but I expect in 20 years people will be doing that. And then you won't need such a complicated thing for gravitational detection. That's my controversial statement. I might be wrong. So this is about what's going on and how does it work. Most of the gadgets of LIGO, why all the mirrors and lasers, it's just to amplify the signal. So if the wave comes through here, you would send the laser there and back, and then you would measure it with the laser that went this way and came back. And the way that the signal happens is space itself is stretched. So in relativity, the space-time interval is 0 for null vectors. And so whatever you do, you can't get into a debate about it. Is the speed of light changing or something like that? It's unobservable. What you measure is that there's a difference between the time the light pulse takes to go this way and that way. Whether it's space or time is kind of your own business. But what you measure is the interval change. So the bigger is better. If you make it 4,000 kilometers or 4 million kilometers, it gets better and better, up until the point that as the light is traveling through the arm, if the space stretches and compresses, then it kind of cancels out your change. And so there's a bandwidth, kind of a gain bandwidth limit, like there's optics or something. So you do want to make it bigger, but if you make it too big, then you'll start canceling out your signal. And people who use pulsars for gravitational detection run into this problem that indeed the supermassive black holes are stretching the whole galaxy, but all of the pulsar signal happens right at the last mile, last parsec. But right before it gets in, it's just the edge effect. All the rest of the space-time distortion gets canceled. You don't get a signal from all. Everything else pretty much is about noise, I would say. So let's say stillness. We're trying to measure 10 to the minus, let's say 19 meters of motion or something like that. And the ground motion is around nanometers, just in a quiet environment. So you have to isolate by 10 orders of magnitude-ish to be able to do this. And that is a lot of complicated engineering, but it's not conceptually difficult. It just, there's a mass and there's a spring, and then there's another mass, and then another spring, and it goes on and on. And eventually, if you have enough masses and springs, each one of those attenuates the ground noise like 1 over f squared. And so you can't do anything with that at DC, but at 10 hertz and above, you can really crush the ground noise. So that's doable. Of course, like your masses and springs have to be sort of special, but it's basically that. We pump out the system, so it's a lot of vacuum technology going on. You get 10 to the minus, close to 10 to the minus 9 millibar, and that's over 8 kilometers of tube of a 1 meter diameter. It's not that big of a deal if you want to do that in the lab by yourself, but it's a lot of struggle to do that for that much tubing, and you often get leaks. So it's a hard engineering problem, but it's nothing that can't be done. The quantum limits come from like the Heisenberg microscope example or the two-slit interference example that you see in textbooks. So typically, you have the electron going through the two slits, and you have a flashlight looking at one of the slits. If you don't look at the slits, then you get a nice interference pattern from the two-slit interference. As you turn up your flashlight a little bit, it starts to disturb the electrons because sometimes photons scatter from the electrons and it washes out your interference pattern. So that's sort of an issue. If you have too much light, you sort of wash out the quantumness of the system and you perturb it too much. And so there's a trade-off where you use enough light so that you can see how much the mirrors are moving, but not so much that your light overpowers the mirrors, scatters them away. You have to do that. And feedback control is the thing you probably never hear about in the context of LIGO because people show you diagrams that are like that one, and there's no feedback controllers there. The fantasy is that those mirrors are just hanging out in space, being quiet by themselves. And we shine lasers at them. They just sort of do it too. But there's hundreds and hundreds of feedback loops that are always operating to make it work. And I don't know why no one talks about that. I think patience is very important. Joe Weber is another figure people don't talk about. I think he didn't really know what all the numbers were, but I think he was taking a sabbatical at Princeton, and John Wheeler and Freeman Dyson were there, and they were hyping up the idea of black holes. And he said, yeah, sure, I can measure that. And at the time, they thought 10 to the minus 15 meters would probably be, that's where the signals are about that strong. If something happens, like there's a supernova next door, let's say, and it's very asymmetric, which they're not. But that's okay. Because he didn't know that stuff, he was bold enough to say, I will do it. And then he made a detector, and he thought he was detecting stuff, but almost surely that they were accidental coincidences, and his data analysis was not that rigorous. It's hard to believe these days, but in the 20th century, people sometimes did things which were not perfectly statistically rigorous. And now we have things like Bayesianisms. And so we understand things like you got to do blind analysis and something like you got to try not to fool yourself. But this was before that time, and so it was easy to fool yourself. And
really quick question: was that first experiment already basically an interferometer? Was it?
It was a aluminum bar like this, and then you would listen to the aluminum bar at the level of 10 to the minus 15 meters, and there was another aluminum bar like a few states over, and the idea was that if they both rang at the same time, it was probably from outer space, as long as you vetoed all the local stuff. And of course, like he claimed there was a detection, and there was a lot of theoretical papers about how that was real, how you could make so much energy. They were wild ideas, they were really good sci-fi ideas in PRD back then, but it turned out not to be true. And then, yeah, Ray had this idea, and LIGO was funded in the early 90s and built, and we ran it for a decade and found nothing. And I just got used to life like this. I thought, this is the life of, if you're sort of a fringe physicist, you just work on stuff that you're not sure if it's real, like axions and WIMPs and all whatever is out there. And like, there was a whole group of us who just worked on stuff that we never found. Like all my buddies were just measuring zero like me. And I thought, all right, this is the life. And no one's ever going to care about what we do. And then in 2015, like right before I went on my first sabbatical, we had the first detection. And I was up here in the Bay Area actually during that time, and people were asking me, what's the, like, there's a rumor, like I saw on Twitter, is there LIGO detection? And so I just learned how to give fake answers. Yeah, it's interesting. And I would give them a bunch of statistical reasoning that would make them bored. So before the detection, we were working on the design, and I'm telling you this story about how bad this was. So I was a postdoc, and I said, let's not build the advanced LIGO like we built the first one, because the first one obviously doesn't work. We haven't found anything. Let's do it better this time. Let's actually try to optimize something. Let's write down what the signal to noise ratio is of the experiment, and then we'll do it. And everyone said, wow, that sounds fancy. How are you going to do that? And I said, well, in MATLAB, there's a function called fmin search, and it seems to always find min whenever I tell it. So let's do that. And then Saul Tucholsky was around, who had written numerical recipes. And he said, that's not the best way to minimize multi-objective functions. And he said, why don't you try these more global techniques like simulated annealing and things like that? anyway, I tried all that stuff, simulated annealing, logic and gradient methods, and like whatever was cool in the early 2000s, I tried it out. But it basically was gradient descent. And that's the advanced LIGO we have today, is my MATLAB code. And that, essentially, we started off with this thing. We said, well, you know, Ray Weiss was really smart, and he said, let's use Michelson interferometer, so we'll use a Michelson interferometer. And Ron Drever, who was also at Caltech, said, lasers are expensive, let's recycle the laser power, and whatever comes out this way, let's put back in. And we use up, we'll get more power. We did that. And in Glasgow in Scotland, they said, well, we can also do that when the signal comes out. Let's send that back in and we'll also resonate that a little more. And that was the whole design process. There's no like global optimization or anything. We just used smart people's ideas, stuck it together. And my job was just to tune, you know, like how big is this thing or how transmissive is that thing? So it was continuous, it's like continuous variable optimization, but over a really limited parameter space. And that's what we got. So that was advanced LIGO, and it worked. It made it
Roughly how many dimensions is for that problem?
like 7.
7?
Yeah. It was really 9, but I didn't realize that most of the parameters were degenerate. So I was solving a 9-dimensional optimization problem where I should have been 7. So, but anyway, I was close up. So, yeah. And then a couple of years ago, we said, let's try this better. And this guy, Mario Kren, had recently published a paper where he had been able to make entanglement out of 3 and 4 photon states, like GHD states, which are, you know, pretty nice for quantum computing. It's really hard to do if you try it in the old way, where you say, I'm going to be really smart and bolt my things together and see what happens. And Mario said, I don't need to do that because I know how individual components work, and I'll just throw it into my box and I'll try every single combination. And his algorithm was so cool that not only does it just try all the combinations, but whenever it finds a subset of components that kind of gets you crawling up the hill a little bit, it remembers that it's a good hill crawler and it saves it in its toolbox. So it doesn't have to reinvent the bicycle all the time. It's like you give it the wheels and eventually it discovers a bicycle. And then now everybody else gets to use bicycles, and then you innovates in that way. And that worked fine. So I said, let's start with this. Let's assume cost is no option and we can build like a 50-kilometer LIGO out of stuff like this. And we started with that. And it discovered these things about photo detection, and we gave it these elements, but it discovered a bunch of things that LIGO people had already found in the 90s. So I thought pretty good, like in about a month, it had rediscovered everything from 1980 up to 2005 or something like that. So not bad. And it had, and we were already seeing some sort of improvement in the cosmological reach. So this is showing something like, here's a vanilla interferometer in blue, and this is a redshift of 1 and redshift of 10. And it's saying that with this more complicated topologies, you can find black holes with masses from 10 to 100 solar masses, and you can get a redshift of maybe 20 instead of 8, something like that. So that's pretty good. That's an interesting region of redshift to explore these days also. But, oh yeah, little animation. So these are the most promising ones, and I don't want to go through each of them, but you know, roughly it's the same kind of idea. There's 2 arms, but some of these topologies, I got to say, I still don't understand what's going on in this one. The laser light comes in, the squeeze light comes in, but then the output goes through this other ring and back and forth multiple times. And it has some interesting aspects, like the system has learned how to cancel quantum back action in limited frequency band. And so what this little graph is showing you here is that the quantum mechanical noise of usual interferometers kind of diverges at low frequencies because its free mass moves like 1 over omega squared or something. But in this one, the back action is actually canceled right here at this low frequency. And right at the low frequency is where the biggest black holes emerge. And so it's an interesting configuration. We're looking at it further, but so far promising. And I'm just saying this large scale method, you know, once you're able to tell it, what do you care about? There are now good methods to, I mean, there's no surprise to this crowd here, but I'm just saying, if you have a good simulator and you have a good optimizer and you know what you want, like you're able to write down your cost function correctly, you can end up with some surprising results. And I think this is true for all kinds of experiments. If you build a seismometer or a magnetometer or whatever it is, just, I know this looks crazy, right? Like, who's going to build that thing? That's nuts. Yeah, it is nuts. But what we did is we built this thing. We said, let's try it anyway. And after we did it, it was nuts, but we did model reduction and said, we'll start with the complicated thing that the machine puts out, but we'll also penalize it for having too many components. And so it learns eventually how to reduce the number of components and give you something like this. And we're still a little bit stuck. We don't know how to interpret this for humans yet. So it's just a solution that popped out, but we need we need people to come in and say, this is what's going on here. Or we could just build it and see what happens. So we don't know what to do. Yeah, onto another topic. So the feedback control is a super, I would say, maybe underappreciated problem in gravitational wave detection. And it has to do with the fact that, like I just showed you, people come up with these crazy ideas and there's no feedback controls in those. So we optimized kind of like half the experiment and just said, yeah, well, like the engineers will figure out that stuff later after we build it. Fundamentally, this is great. Yeah, but it's fundamentally doesn't matter. What matters is what matters, right? So what matters is, sure, the quantum mechanics and all these things, but you have to be able to actually run the experiment. And the way LIGO works is, everything is like, it's like balancing a pencil on your hand like this. And then there's like 100 more pencils on top of that. And you're just going like this all day. You're trying to spin all these plates all the time. It's a nutty feedback controls problem because all these different degrees of freedom are talking to each other. And physicists are not we just don't know how to handle that kind of thing. If you have 100 by 100 multiple input, multiple output system, which is, dynamically and statically unstable, how do you handle that? And we've always handled it by just doing one at a time and just hoping, like the little boy putting his finger in the dam, that it's just going to work out. And so far, so good, but the performance is suboptimal, I'll just say. And so we reached out to Google DeepMind, and they said, hey, we're into this AI for physics stuff. What have you got? What's an important problem? And we said, well, this, like, how do we control LIGO and keep it from going unstable all the time without polluting the noise, where the black holes are? And so we've been working on this since 2022 or so. And the goal was always, we're finding a bunch of little black holes that are, the masses are sort of under 10 or 20 solar masses, but my dream has always been to use this to do cosmology. And the best you could do, if you found something like 1,000 solar mass black hole merging into another 1,000 solar mass black hole, you could see those at a redshift of about 15, which would be spectacular. It means we'd be probing that interesting region from Z of 10 to Z of 20 and doing it with black holes for the first time. And that was the only hope of really doing cosmology with LIGO, because all of the little black holes, you can see it to a redshift of like 3. And that's cosmology, I guess. But, now there's JWST. So like, I feel like the bar for what's considered cosmology is Z of 10 and higher. So that was the goal here. And the problem is that the existing feedback controls limit the sensitivity of that band. And so I like to show this picture just to say how remarkable this is. In this top row is Caltech and our collaborators in Italy, GSSI. There's only a few of us working on this. The whole team is basically Google DeepMind. And so they were extremely generous in giving us this many people to work on this problem for 3 years. It's a lot of effort, but they really believe that this was going to pay off and be useful. And I thought at the beginning, maybe this would take a few months. I mean, how hard, like I know FMIN search. So how could this be that much harder than that? It was really hard, actually. It turned out like all of the different stuff that we had to solve to make it actually work in real time. And the problem we solved is this one. So the LIGO mirrors are a little bit curved like this, they're a bit concave. And when they tilt like this laser beam and that laser beam push on the mirror and try to make it go backwards. So the mirrors are sort of doing this kind of action. And because they're curved so much, if you move them just a little bit, the beam moves around a lot. And that means it's like a torsional bar. The radiation pressure from the light is a torsional restoring force on the mirrors. And because of the finite travel time of the light, it's actually dynamically unstable. So the radiation pressure links all of the LIGO mirrors. And by the way, each one is 40 kilograms. It links all of the LIGO mirrors into this 8-kilometer optical bar thing. That's actually what the interferometer is doing by itself. And it's really hard to control it because this resonance is at kind of a high frequency and it's very close to the observation band. So we're trying to control this motion and we're also trying to observe gravitational waves, and the noise from the controller is getting into the band and converting this. So this is what we did. I spent a lot of time carefully measuring the LIGO interferometer to find out how it behaves. And we made a model based on that. And then the DeepMind people ran this, millions of times, and I don't know how many CPU hours were spent, but probably a lot. For the first time, we used frequency-dependent rewards. So we rewarded the system if it was able to suppress the vibrations at the low frequency, and also if it did not mask gravitational waves at higher frequencies. And so there was this reward loop, maybe a lot more details in the implementation if you want to hear about it. But eventually, through this reinforcement learning, we were able to make an agent that actually was able to do the control. And in the real-time LIGO system, we would switch between the usual linear feedback system and the neural network policy periodically just to see what the difference was. But almost all of the training was done offline, and then we actually ran it on the real LIGO system. So you can maybe see on the left what the problem was. That red trace is the control action, controlling mirrors like this. And at like 10 to 20 hertz, it's about an order of magnitude worse than the quantum mechanical limits, but just from sensing. And we had been working on these feedback loops for decades. I spent a lot of time just thinking, will the low pass filter be at 8 hertz or will it be at 8.2 hertz? Like back and forth and back and forth. And you can just imagine it's just like me. You can put 1,000 physicists there with 1,000 knobs and just do this all the time, but you're never going to get the best solution. You're just never going to get it. And it's because the problem is not convex optimization. Usually people think if you have a 2D Pareto front or something, you can make it into a convex optimization problem if you use FIR filters like the equivalent of CNNs, that it's convex. But it's not truly convex. If you have too many CNNs, it's not a convex optimization problem. And similarly for LIGO, it's not convex. And so we're never sure if we're really getting to the best result. And so we use this method. And on the bottom left, you can see what the network is. There's some inputs. We look at the past, kind of few minutes of data. There's dilated convolutional layers and then just usual FFP. And then anyway, so we ran it on the plant. We use this kind of reward system. We also asked that it not saturate or other sort of safety things. And the final controller that we got is, in this band where we're hoping to find gravitational waves, it's more than an order of magnitude better than the linear control. So this technique now makes it so that feedback controls is out of the picture. But maybe even more interestingly, you can see down here, like below where we even thought about looking at, the controller has found, another order of magnitude improvement. So it means if we could improve the mechanics of LIGO, like the suspension systems and the vibration isolation, we could go even lower. And so that means, let's see, so at 12 hertz, if you detect a merger, that corresponds to a black hole of 1,000 solar masses. So nobody even talks about this really, but there's a big gap, right? We've detected black holes of sort of a few hundred solar masses, and at the center of galaxies, there's things that are like 1 million. And between there's 2 and 6 on a log scale, and there's other numbers in there, right? There's 3, 4, and 5. Where are they? And what are they doing? And where do they come from? And so this is our hope, I think. If you
just to clarify, the purple line is experimental data. This was it was put in production. That's not the prediction of the CNN of this fancy RL.
Data. That's right. So the prediction kind of looks like this.
Yes.
But the first 95 times we tried it, it did not work because my simulation of the plant wasn't good enough. And so I just more and more and more figured out what is going on. And it had to do with the fact that the plant parameters actually vary with time, and they change due to the thermal state of the instrument. So if you do something bad, and the laser turns off or something like that, the mirrors get cold. And when they get cold, they get more curvy like this. And when you heat them in the middle, they kind of get flatter. And then this dynamics of this jittering around, it changes depending on this curvature. So we were kind of hurting ourselves in our own video game, essentially. We're like heating and cooling LIGO in a bad way, and it's hard to train in that condition. So we had to do this physical plant domain randomization, where I said, I don't really know what the curvature of the mirrors is. I don't know exactly what the laser power is. And I need this controller to work under this broad class of random systems. And I kind of give it a range and let it train over that range. So it's now able to adapt. So
It's robust within that boundary.
yeah, within that boundary. And it has surprising behaviors that we still don't understand. But this data is from running it for about an hour on the LIGO detector. And it's no drama. It just kind of ran. Nobody knew what was happening. And then we said, okay, thanks. And then let's publish this thing. So that worked to 1 degree of freedom. Our next thing is to use it on multiple degrees of freedom. But essentially, this whole gap between the LIGO performance and this green line is a bunch of curves like this red one. There's a bunch of other curves here that are controlling other degrees of freedom. And so we'd be able to knock out all of those and then hopefully get to that green line. And then that's when we'll really find massive black holes.
Please give more details for the rewarding function.
The reward function?
Yes.
Yeah, there's a few other rewards, but this is the main rewards. So this is this spectrum here is about how much is the mirror moving in an absolute sense. And this curve is about how much torque we're applying to the mirror to control it. And so what we want to do is minimize this spectrum multiplied by that filter. And then this spectrum multiplied by that filter. So we're trying to select basically for the RMS and the low frequency band of the mirror motion. And then in this band, that just corresponds to this band.
Oh.
So the idea is in the band where you're observing gravitational waves, you don't want to add back any noise. So we minimize just that band. And then you also want the mirror not to move too much, otherwise the laser power drifts too much. So we minimize those two. But I mean, now that I say it like this, it seems kind of childlike, I guess. Like this is too much humans in the loop, I think. What you'd prefer to do is just have, run the full video game of life. Say, whatever matters, your simulation ought to be able to tell you, right? So you should allow the controller to do anything it wants and not have to give it these specific things. What you'd like instead to do is put in simulated black holes into your simulation and have it just pull out the signals and not just control 1 degree of freedom, control all the degrees of freedom and do the analysis and publish stuff on the archive, maybe, or something that, like as much as you can, you want to go from beginning to end. And doing this kind of thing, I don't want to do that again. I hope this is the last time we publish these sort of individual rewards. Like reward engineering, it feels a little bit like feedback loop engineering, right? It's like, where are you moving the intelligence? And I'd like to be I don't want to be part of this. I just want to say, give me the astrophysics and then do it. And like, it should be able to do it. But right now our model does not learn from the experiment. So the next thing to do is really train the model on the real data in a smart way. Yes, so in the next 5 minutes, I'll try to tell you about this very detailed problem, but essentially it's about the mirrors. So quantum mechanics is a limit, but the quantum mechanical limit has nothing to do with the mirrors right now. The quantum mechanical limit has to do with the vacuum fluctuations of the electromagnetic field, and that we compensate for by squeezed light. But then now that that's done, the issue is that the mirror is just vibrating too much. And we've isolated from all the external vibrations. So the vibrations of the mirror have to do with its own internal motion. And that's just thermodynamics. So you have 1/2 kT of energy per mode, right? But think about it, if your mirror has an infinity Q, like it's perfect glass, the perfect wine glass in the world, if you ping it, it'll just keep ringing forever, right? There's nothing to stop it. But the reason it stops is because there's some dissipation. So the acoustic mode phonons in your wine glass travel around in your glass and they couple to the background heat bath and some of the energy goes into the other modes of the glass. And so you are dissipating your energy into those modes. And because you can dissipate energy into your modes, it means noise from those modes can come backwards into the mode that you care about. And so, I don't know, I guess if you had the perfect wine glass and nobody else was talking, you could just listen to the wine glass and you would hear the Brownian motion of the wine glass, if you could hear so good. And that's kind of the LIGO problem, that the wine glass, which is the glass mirror, is vibrating too much at the modes that we care about. And what to do about it? So we try to make the best glass in the world. So the substrate itself has a mechanical quality factor of 10 to the 8 or more. So that means if you ping it, it goes 10 to the 8 cycles before the energy goes down by half. So that's really, really good. But that's just glass. And to make it into a mirror, there's a thin film on the front surface. And that thin film moves back and forth. And the film is like this. So as I said, this is 10 to the 8, but the film on the surface only has a Q of about 10 to the 4. And so that means its coupling to the heat bath and the other modes is 10 to the 4 times worse, which is no good. And why is it like that? There's a lot of conjecture, but for whatever reason, it is bad. And that is the fluctuation dissipation theorem, which says essentially, I mean, in equation form, it says what I just said. So it's kind of like the Fermi's golden rule. So if you're coupled to, I guess it's pre-Fermi. There's the actual kindergarten golden rule, right? Like, do unto others as you would have them do unto you. That's what you learn. And that's what Fermi's golden rule sort of means. It means the photons which scatter off of some sort of transition or atomic system, it also tells you about how much that thing will absorb radiation and couple it back to you. It's just talking about the time reverse symmetry in that system. And the fluctuation dissipation theorem is like this. It says, if you care about the fluctuations of your system, the power spectrum of this motion, that has to do with the admittance of your system and the temperature and the frequency. And the admittance is just the ratio of the velocity divided by the force, if you apply force to it. So you take your system and you squeeze it like this, and you see how much heat is generated. And that tells you how much dissipation is in your system. And that will tell you how much your system will fluctuate. So that's what we do. And so this is my proposal, but I'll say to you, we've been working on this problem of trying to make perfect thin films for about 20 years. And no matter what we do, at room temperature, all the amorphous oxides that we've tried have a mechanical quality factor of like 10 to the 3, 10 to the 4, something like that. But there's almost universal. Everything that you find is like that. And if you do it wrong, there's a lot of things that can go wrong, but even the best films, they seem to be limited by 2-level systems in the thin film. And the issue with the 2-level system is it's like this, you have, I don't know, like inside of the film, there's some molecules that can flip back and forth a little bit like this. And they might have oscillation frequencies that are like a few gigahertz. We're making our measurements at 100 hertz. So what does a gigahertz matter to us? Well, if you're in other worlds, like you're in superconducting qubits or axions or something like that, the 2-level systems are directly in your band. For LIGO, they're way outside of the band, but it's the tail of that peak up at a few gigahertz that matters to us. And the issue with the 2-level systems, it's a little bit anharmonic. If it's a fully linear system, it doesn't really matter. The 2-level system up there wouldn't dissipate anything. But because the potential is a little bit anharmonic, when you strain it at 100 hertz, that modulates this potential of these multi-gigahertz resonances, and it's able to couple energy back and forth between these two. And we've tried all kinds of things like annealing and trying different compositions and different metal oxides. But the issue is the process is really, really slow. And none of this exists. So we have deposition and we have some characterization, but this process takes, let's say, a few days at best. Because you have to grow the film slowly. You need to make a stack like that picture I showed. So at the best, it's like 3 days or something to grow a film. And then the manufacturer usually does some characterization too. And then you ship it to a bunch of university labs. And depending on the grad students, how they feel that day, and like, do I have funding or whatever, that's a year, And then we don't have a physics surrogate model. We have Marty Fayer over at Stanford. who has a big brain. And we just sent him these things and he says, well, how about you try this? And then it goes back and this doesn't exist at all. And then it goes back to this process. So our feedback loop time is like years on every cycle. And so you can imagine maybe in 25 years, you haven't made a lot of progress. So I think this is what we need now. We need to resuscitate solid state physics so that people can make these kinds of good models that are physics based. And then they're super expensive to run, right? I think they're like DFT simulations with 100,000 molecules is really expensive. But if you could do that, you could build surrogates on this. And the surrogates need to know about this. And this is usually the mystery, that what is going on in the deposition chambers. So we're using ion beam sputtering, you know, just like the ring laser gyros used and everybody else uses for high quality optics. But the behavior of the chamber really depends on what's been happening in the chamber for the last few months or something. And usually there's a person, there's no robotic person, there's like an actual person who's having to do this. And if that person isn't really, you know, on the ball that week, then who knows what's going on. So there are a lot of hidden variables in this. But you need something like your surrogate model to be able to figure out the hidden variables over time. So you need this part of the system to always have calibration going on. So you really get what's going on in your process. And you need your model to know about this thing. And if you can do this completely robotically, and you have all the characterization in situ, you can get this 2-year cycle time down to something like 2 weeks, because the measurements don't take any time at all. So this deposition plus annealing, you know, for sure we can get it down to a week, maybe a few days or something like that. And depending upon how many of these things you can run in parallel, you can now think about making order of magnitude improvements in the thin films that we have. I think, although, like I said, I'm not a condensed matter physicist, I may be wrong. I was trying to think of what are, like every time I have a good idea, I feel like I go talk to somebody smarter and they say, yeah, no, that's not. So this is all the reasons I thought maybe it wouldn't work out. Mainly, so if you look at 2 through 7, maybe these are the common things you know about. It's hard to scale to large sizes. When you build your surrogate models, it may miss the hidden variables. I think we can capture the hidden variables if you do enough interfacing with the deposition equipment. It's hard to get this kind of thing, like random defects falling from the chamber and making little scratches and things like that. I think, of course, people have to be involved in making sure your equipment runs well. I think the number one thing is I've listed as number one, we don't really have a good microphysical model yet for how mechanical loss works in thin films, but that's a thing to be developed. And I think just, you know, like these days, we don't have a lot of solid state physicists who are sitting around and studying these things, but it was a hot topic in the 70s and 80s. So maybe it's, you know, like bell-bottom jeans are coming back. So solid state, you know, there can be hope. So I think these things can kind of be solved. These are legitimate problems, but they're just, I think it's just work. There's a lot of prior work on this. So at UBC in Vancouver, they have this thing called a self-driving laboratory for thin films. And they had a particular goal, which was not this mechanical loss stuff, but there's a few other groups in the world who have done thin film optimization. They've used surrogate models. So all the pieces sort of exist in a bunch of different labs, but nobody's yet trying to do this for the specific goal of making the ultimate film without 2-level systems. But if one goes for that, I think it'll solve the problem with decoherence in superconducting qubits, because they also use these high index films, and then also the LIGO thermal noise problem. I know I'm out of time, but this is just part of my plug. This is like when somebody's on the Tonight Show, they plug their project. I've been working on making a LIGO in India since 2008, and it's a lot of freaking flyer miles to do it. But you know, I had to wear a suit and everything. But at the end, we got funded just a couple of years ago. And so the Indian government's giving us $300 million to build a 3rd LIGO. So, you know, good for us. I think, I don't know if that pays for all my flights, almost. And there's a lot of things going on in gravitational waves. People are build bigger detectors in the future, but within, sort of the next 5 to 10 years, what's going to be the next hot thing, this is it. So we're going to add this detector in India. It's going to change LIGO from a 2 thing to a 3 thing. So you can use the word triangulation if you have 3 things. And so we'll be able to tell where things are on the sky. We'll be able to figure out the polarization of the gravitational wave signals and also detect a lot of signals from just having a lot more uptime. So all of these AI tools I'm talking about, like optimization of design and feedback systems, it's really meant to be implemented in this new Indian detector because we'll turn it on and there's no reason to go through the process of, having 50 people sitting around and pressing a bunch of buttons. But you can automate the whole process of, once you've bolted it together, you kind of want an auto-tuned LIGO interferometer. So that's the dream. And I will close here with this inspirational message, which I like to make up quotes for myself. I think there's a lot of things that can happen, and it's just, as I've seen it throughout my scientific career, if you just get kind of like a couple dozen people excited about a topic, it's incredible leaps and bounds you can make. And I think this thing of using machines to design better machines is one of those things. So thanks for your time.
Thanks so much, Rana.